numerical modeling and experimental investigation of the charging and dynamics of dust in astrophysical laboratory plasma environment. And as you can see from her title, she will talk about cosmic dust bunnies and laboratory dust crystal. So, Professor Matthews, it's a pleasure to have you here, and the stage is yours.
Thank you very much, Luciano. So I was going to give you a little bit of an introduction about how I got to where I am. In high school, I was very interested in science, but I was really good at biology. And I actually ended up studying chemistry when I came to Baylor for university. But then I had some amazing physics professors who talked me into changing my major to physics. And so I got a National Science Foundation fellowship for my graduate studies, and I continued my work here at Baylor. And after I got my PhD, I then went to work as an engineer for Raytheon Aircraft Integration Systems. And one of the main projects we were working on at that time was redesigning the Boeing 737 aircraft to hold the NASA SOFIA telescope. And so it's a major engineering effort. You can see it has this garage door that opens up, and looking out with this telescope that weighs 40,000 pounds that you're trying to keep steady to do science. After 2 years of working as an engineer, my graduate advisor, Dr. Toole Hyde, was starting CASPER, the Center for Astrophysics, Space Physics, and Engineering Research. So I came back to Baylor to be a scientist with that collaboration. So we've continued to work together for the last 22 years. And I have my own research group now where we're doing the numerical modeling of dust and how it charges and how it agglomerates and forms larger structures. My research is currently funded by the Department of Energy and the National Science Foundation. And this is a beautiful picture taken by the NASA SOFIA telescope that shows the polarization of light by dust that then is mapping out the magnetic fields around a black hole. So it all comes together. So let me tell you a little bit about plasma parameter space, because plasma you think of as being very hot, like the sun is a plasma, but actually it can span orders of magnitude in temperature and in density. So the plasmas that we see in space, like comet tails or the plumes that are being ejected from Enceladus, are very cold plasmas. The noctilucent clouds that are visible at high latitudes on Earth are also very cold. Whereas if we're looking at something like the solar corona or the plasma that we're creating in fusion reactors to mimic the interior of the sun, are going to be very hot plasmas. And they can range from very low density, where you only have a few ions per cubic centimeter, to extremely dense plasmas. So we have a large range of scales to play with. So what is a dusty plasma? Well, you know that if you add energy to a gas, you can ionize the atom so that you have positive ions and electrons. And then if you put solid particles, the dust component, they will actually charge up, they'll collect electrons, and they will attract the ions. And there's a certain characteristic distance called the Debye length. And the Debye length characterizes kind of the density of the plasma, the charge on the dust, so that when you take the normal Coulomb potential, 1/4 pi epsilon naught times the charge divided by the distance, you actually add on this exponential term that provides extra shielding, so that the Coulomb shielding falls off exponentially with the characteristic scale length of this Debye length. So why are we studying dusty plasmas? Well, 99.99% of the universe is in the plasma state, or the visible universe is in the plasma state. And then we just have dust contaminating everything. So here's a picture of the Eagle's Nest Nebula, where we have clouds of gas and dust, and we have stars forming in those regions. And once you have formed a star, you're left with this debris disk, or a disk of gas and dust around the star. And this is where you're actually going to form the planets. So here you can see the disk is seen as this dark band that's obscuring the star, and then you see the light that's being refracted around that. We also see them in our solar system. This is a picture of Saturn's F ring, which is just outside of Saturn's main A and B rings. And these rings are very dynamic. They consist of very fine dust. This is one of the shepherding moons, Prometheus. And you can see that the dust is then not only going to interact gravitationally with the moons, but it can also interact with Saturn's magnetic fields because it's charged. Then we can see comet tails, and even dust is lofted above the surface of the moon, which provides this lunar horizon glow. Since the moon has no atmosphere, we wouldn't expect the sunlight to be refracted because there's no gas there to do that, but the dust itself is lofted above the surface of the moon. Then where this became really important was in the silicon processing industry, because the way that computer chips are made is that you actually use plasma to etch these very tiny features into the computer chip. And when you etch the material, you actually create dust. They spent billions of dollars to do this in clean rooms because the dust can be small enough to actually be larger than the chip features. But then they found that the dust was actually being created in the process themselves. So they created a particular type of platform called the GEC reference cell, the Gaseous Electronics Conference Radio Frequency Reference Cell, so that they could study this effect. And so it's a vacuum chamber that usually we put an argon plasma in, so it has this nice, pretty purple glow. And then being the dusty plasma physicist, we put dust in it on purpose. So why are we doing this? One of the main questions that we want to answer is, are there other solar systems like ours? Can we find another habitable Earth-like planet? And there were certain characteristics of our solar system that we find interesting, that we have rocky planets close to the star and gas giants very far away from the star, and we only see liquid water on our planet in what we call the habitable zone. And other solar systems that we found don't look like ours. And so we're interested in the processes that occur that allow planets with all of their different variations to form. So let's look at some of these planet forming regions. If we look in the constellation of Orion, this is a visible light view, but if we look in the infrared, then you can see all of the gas and dust that is surrounding these stars. And if we zoom in and look at the Orion Nebula, we see all of these regions where stars are forming. They're inside their own little shells of gas and dust. And after they've blown off a lot of this material, you're left behind with just the disk and a newly formed star. So we've seen these circumstellar disks before. This is where we're going to form the planets. And with the Atacama Large Millimeter Array in Chile, we're actually able to resolve these disks and see that there are ring structures and gaps that we think are associated with planet formation. So why are we building dust bunnies? Well, this is the very first step in building a planet. You have this gas and dust, and we have to form the dust into larger clumps, and it just kind of sticks together like the dust under your bed and forms these large fluffy structures. And we want to understand how these large fluffy structures can grow larger and larger in size until they're actually able to attract each other gravitationally. So I'm interested in calculating the charge on the dust and then how that charge changes the collisional growth of the dust grains. So if we look at some of the processes that are occurring in the stellar disk, here we have a star, and then we have this disk of material that is orbiting the star, and the disk actually kind of flares and gets thicker as you go far away from the star. Well, within the disk, the dust particles can just be moving around because of essentially Brownian motion. But we also find that the material on the disk vertically settles towards the midplane of the disk. And then there's also this radial drift that all of the materials is losing energy and drifting into the central star. But then you get more complicated processes that occur, and you get turbulence that also stirs up material in the disk. So we can have lots of different processes that are going to drive the relative motion of the dust. So let's look at the charging. So if we have a dust particle, how does it become charged? Well, the first way it becomes charged is just by collecting the electrons and ions from the ionized gas. These are what we call the primary currents. And the electrons move faster than the ions do. And so the dust will tend to collect more electrons than ions. But there's other processes like secondary electron emission, so that if you have very energetic electrons, then they will actually tunnel into the material of the dust and knock off other electrons. And this is a net positive charging process. And then we can also have photo emission, where you have high energy photons from ultraviolet or X-rays that actually then knock electrons off of the surface. So we can actually write an equation for the charging current. You're basically looking at the flux of material that can come in from all possible directions with all possible speeds. And if we know the current tells us how the charge will change in time. And then the charge is related to the capacitance and the potential of the grain. And so it all feeds back into the charging currents into this loop. So we can actually do these calculations analytically if we have a sphere. But if you have something like a dust bunny, this integral, which is over all the possible directions that the dust, that the ions and electrons can come in, becomes a little bit more complicated. Because if we look at a particular point on a dust grain, you can see the electrons and ions can only come in from certain directions and hit this spot on the grain. So that's what we do numerically using what we call a line of sight approximation. So only if you can look out from a particular point on a grain and have an open line of sight, you're not obstructed by other parts of your fluffy dust bunny, will you actually be able to charge. And so this allows us to resolve where the charge is on the structure and even on the surface of the individual subunits within the structure. And this is what allows us to get some very rich dynamics. So first of all, we can look at how the charge changes in time. And you notice that most of the charge will go to the extremities of the dust bunny. And you can also see that if you have a range of dust sizes that are forming the fluffy dust bunny, that the larger monomers within the aggregate will hold more charge than the small ones, because they're acting like little capacitors. So if we put this together with our dynamics, what matters is the time scale. If you have a lot of plasma and the charging time is very short, then the charge on two colliding aggregates will change as they are colliding, and you will get a particular outcome and build a particular type of aggregate. However, if you're in an environment like space where the charging is very slow because you don't have a lot of plasma, then the charge remains fixed as particles are colliding, and then you can have very different collision outcomes. So we want to look at all the different processes that will cause these collisions. And so we can look at how turbulence is driven in the disk, how that drives the relative velocities, and how that changes the relative charging times and the relative aggregation times. And so you can build dust bunnies in different environments. This is an example of a dust bunny that's built in an environment where you have a lot of charge and the structure is very open and fluffy. And this is a dust bunny that was built in an environment where the dust wasn't charged at all. And so you collect a lot of the very fine dust, and it's a very compact structure. And so these will behave differently than when they start colliding with other materials. And one of the ways that we can actually study this here on Earth is looking at meteorite samples. The meteorites that fall to Earth have been in an environment where they have very minimal processing of the rock. And so these were rocks that were formed at the early stages of our solar system 4.3 billion years ago. And if we find them early enough, they haven't been changed very much on Earth after they've landed on Earth, and we can cut them open and examine the types of rock that are inside. And one feature that we commonly see is that a lot of these meteorites are called chondritic meteorites because they have these little millimeter-sized inclusions called chondrules. But the interesting thing about the chondrules is they have this rim of material around the chondrules. And this rim of material is very different from the solid interior of the chondrule, and it's formed from very fine dust. So one of the things we can look at then is how do you build up these fine-grained rims on top of the chondrule surface? And then can we relate the environment that the rims were formed in, looking at the ionization of the gas and the turbulence level in the gas to figure out what kind of rims do we form and how can we compare these rims to those that we see in meteorites. So to do this, we need to know a little bit more information because how did the rims get restructured, say, when they're colliding, or are our models even accurate for the way that we're laying down the dust on the rim? And so we turn to the lab to do that. But I'm actually going to look at even more fundamental interactions between the dust and the plasma and how we can actually form ordered structures. So we're going back to the GEC reference cell here, which is these two electrodes actually form a capacitor, and then we alternate the current on the two electrodes at radio frequencies, and this actually excites the electrons and gives them enough energy to ignite the plasma. So the plasma is this kind of purple glow, and then this pink stuff you see right here is the dust that's illuminated by a laser. It's micron-sized dust. To give you a size of the scales, the width of a human hair is 100 microns in diameter, and we're looking at dust that is 10 microns in diameter. So one of the interesting things is if you look at this dust from the top, we actually have a camera that looks down through this hollow electrode, is that the dust, when it becomes charged, can actually form a crystalline solid. And we can do experiments that are analogous to atoms in a real solid where we watch phase changes and you can see the crystal melt or then become a gas. But one of the things we want to look at is how do we aggregate the dust particles? And so to do that, we put a glass box on top of our electrodes so that we can squeeze more dust together and excite density waves in the dust, and the dust will actually collide and stick and form fluffy aggregates. It's very hard to see the collisions. Using a high-speed camera, that's running at several hundred frames per second, you can watch this, and then you're looking at minutes and minutes of video when you play it back at 30 frames per second that we can watch. And here's an example of a collision where you can see the two particles are rotating as they collide and stick, showing that the charge is arranged on the surface, and we get these dipole-dipole interactions that cause it to rotate. Then after we turn off the dust density wave and we're just looking at the aggregates that are left, we see that we get these very elongated open structures, but they tend to rotate. And we're like, why are they rotating? What is going on here? This is seen in experiments even where you don't have plasma. This is another experiment taken where they're using something called thermophoresis, where they have a temperature gradient that's helping to levitate the dust particles. And they also see those particles rotating. So we can use these 3D images as they're rotating to reconstruct models, and then use our computer models to figure out what are the forces acting on the grains. And if we add in this extra, say, thermophoretic force that's caused by this temperature gradient and the gas that's coming up from a hot electrode having a slightly different velocity from the gas that's coming down from the cold electrode, we can see that we have competing torques acting on the dust grain. So this arrow shows the direction of the electric dipole moment, and the torque from the thermophoresis, which is acting on the geometric sites on the grain, will cause this to go slightly off from the vertical, and this causes the rotation. So a lot of what we find out is that we really don't understand the plasma at all. Especially because what happens is most of our experiments here on Earth occur right down at the bottom in what's called the plasma sheath. And the plasma sheath is where you've got the edge of the plasma and you've got all these crazy edge effects going on. But when we put the dust into this environment, we can get very ordered structures. And so here we are forming a single dust chain as we drop the dust in, or with slightly different conditions, we get lots of dust chains. And these structures may or may not be static. So here's a double dust chain, but it decides it doesn't like being a double chain. It goes to a single chain and it doesn't like that either and goes back to the double dust chain. And this will sit there and do this for minutes. Or we can form very stable structures. This is actually a video of 3 chains right here, where you view it from the top and you can see that you have 3 particles arranged in a triangle. And by changing the plasma just very slightly, you can get it to jump from one stable structure to another. And we're looking at this going, why do the particles line up this way? What is going on in the plasma? So we have to look at this plasma sheath region. Up here in the plasma bulk, we have a conducting fluid. And remember that inside of a conductor, the electric field is 0. And the number of electrons, the number density of the electrons, is essentially equal to the number density of the ions. And so this is neutral up here. But I said that electrons run into everything and it becomes charged negatively. So the electrode actually is charged negatively and it repels the electrons from that surface. And the ions, which are positive, are then accelerated towards the surface. And so we get the plasma sheath where the number density of the electrons doesn't quite match the number density of the ions, and we have this electric field. And we use this electric field then to levitate the negative dust grains against gravity. So what becomes important then is we're levitating the dust grains against gravity, but we always have this ion flow that is flowing past the negative dust grains. And the ions, which are positive, then get deflected and concentrated in a region downstream of the dust. And we call this the ion wake field. And it's characterized by the Mach speed of the ions, which is the ion flow based on the sound speed in the plasma. And this wake field feature is ubiquitous across nature. We can see it in water waves behind a rock. We can see it in waves here in clouds in the atmosphere behind the Eel Amsterdam. We see it in space. This is a wake behind a neutron star called the Guitar Nebula, as it has this shape right here. And then this is a wake from one of our numerical models showing the density of the ions behind this chain of dust grains. So we have a large group that's working on our numerical models. It takes a lot of people to put all the features in place. And so what we're looking at is we're trying to simulate the ions in the plasma as they're flowing past the dust grains. And we're looking at ion forces, ion dust forces, how the dust is charging, if you have multiple dust grains, how that changes everything. And so we can build up a picture of the density of the ions, they're attracted to the negative dust, and then also built up in the wake downstream of the dust. So here's a model of our dust and ions where we can only see the 2 dust grains. And this is what we would see in the lab if we had 2 dust grains and then we ping one with a laser to knock it out. But with our models, we can also see what the ions are doing, and we can actually see the ion density forming wakes downstream of the dust. And then what we're interested in is the potential. So here we have a positive potential region due to the ions and a smaller positive potential here. And so the negative dust grains get attracted to these positive potential regions, and this helps form the structure that we observe. But gravity is a nuisance because, as I said, all the dust chains want to line up vertically. and gravity is acting vertically. So we are always having this really large force gravity that we're having to subtract from all of our data to figure out what these tiny dust ion forces are. So we turn to the International Space Station and do experiments in microgravity. So we have a slightly different plasma. It looks like a neon tube because it is a neon tube. This is actually a neon plasma that's lit up, and we have electrodes that are here and here. And this is a DC plasma, so the ions are always streaming in one direction from the cathode to the anode. So to compensate for that, because we don't want the dust to be streaming back the opposite way, we alternate the polarity on the anode and cathode really fast at 500 hertz, so that the ions can change direction, but it's too fast for the dust grains to change direction. So this is what the experiment looks like in a cartoon. We have this region of a glass tube where we have dust shakers on the side, and they come into the viewing angle where we have our cameras, and then turn on the polarity switching to trap the dust in this region. And then using the cameras, we can actually see what the dust is doing. We actually have a laser sheet that's vertical that's going through the plasma. So you only see a small slice through this three-dimensional dust cloud. And so this is done on the International Space Station. Usually the Russian cosmonauts are running the experiment. And then we have people that are in the mission control in France that are talking to the cosmonauts, saying tweaks to the script for the experiment that we're running. So we need to understand the plasma. So we have a PIC model of the plasma that tells us what the potential drop is, and we can look at the number density of the electrons and the number density of the ions, and then we were just modeled the dust right here at the very center. And if you look carefully, you can see, oh, there's kind of blobs of electrons and ions. And so from the numerical model, you can actually see that, yes, you do have these blobs of the plasma, and they actually are moving. So this is from the simulation. You've got the blobs, and then 10 microseconds later in the simulation, you can see that the blobs have changed in time. And so one of the questions we wanted to know is this a numerical artifact, or does this actually exist in the plasma? They're moving really, really fast. They're on a microsecond time scale. So we have a ground-based mock-up of the International Space Station experiment. And if we look at the blobs and where they are in the tube as a function of time, we can see that a blob is going to move in time. And using a high-speed camera in the lab that's running at 50,000 frames per second, we actually detected those blobs in the experiment. So the numerical model showed us something that we didn't actually know what was going on in the plasma. And so what happens is the density of the electrons and the ions is actually not constant in time, but it's varying very rapidly on the microsecond timescale. But the dust can only move on a millisecond timescale. So we're wondering, does the dust even care? Can't we just average all this and ignore it? We ran several models of the dust and ions. You can see that the dust lines up in chains and forms rather stable structures. But then we can also look at the ions, and what happens is then the ion density is going to change in time. You can kind of see it pulsing as these ionization waves are passing. And so it makes even stronger ion wakes, and it's the stronger ion wakes that allows the dust grains to actually line up in chains. So if we run larger simulations, we can look at a whole cloud, and we can look at structure and how structure would form in time. So these peaks actually show that particles preferentially will form at a certain distance away, and then this is the angle. So that's analyzing the numerical data. And then we can also reconstruct three-dimensional data from the International Space Station, and we see the same sort of peaks in distance, telling us they're lining up in chains, but then they're also at specific angles, which gives us the order throughout the three-dimensional cloud. From the numerical data too, we can always label all of our particles, so we can actually see that the particles are actually form these nested cylinders. And remember, I said that from the space station data, we're only getting a vertical slice, But by scanning the laser through the cloud, we can get lots of vertical slices and stitch them back together. And we also see these nested cylinders in our experimental data. So we're still putting all of this back together. And it's kind of interesting, though, but we have this structure of the universe here that's wrapped up in the structure of these tiny dust particles. So we're trying to use what we can see, the microphysics level, and then extrapolate that into how that is going to affect the formations of stars and planets and all the structure we see in the universe. So thank you very much for your attention.
Thank you very much, Lorin, for being perfectly on time and giving us opportunity for questions. So I invite all the attendees to formulate questions. And there is a first one by Del2 and says, Dr. Lorin Matthews, did you consider more generalized distribution other than Boltzmann distribution when modeling dusty plasma? If so, did you notice any significant change?
Yes. So for the plasma in space, it often has what's called a kappa distribution or a Lorentzian distribution. And the difference there is that you have a high energy tail on the electrons and ions. And so with the high energy tail, you have more of the energetic particles, especially the electrons. And so you're actually able to collect more electrons because they're not repelled from the dust as easily when they have more energy. And so you actually get stronger charging in a Lorentzian plasma than you do in a Boltzmann plasma. And in the lab, it makes a big difference because it's really not a Maxwellian plasma or a Boltzmann distributed plasma. Because you've excited these electrons, you actually have an extra population of high energy electrons. So there's all sorts of different distributions for the plasma particles and their velocities.
Okay, thank you. I don't see any other question. But I have a question, if you allow me. So you mentioned gravity is a nuisance, as a gravitational physicist. That's, the first time I hear it.
Yes.
I know we try to put it in as strong as possible. But normally there is another thing that in astrophysical plasma is all over the place, and that's magnetic fields.
Yes.
You haven't quite mentioned this. What is the role that magnetic fields has in your calculations?
Okay, so the magnetic fields play a large role in the protoplanetary disks because the MHD models give this magnetorotational instability, and that's what is hypothesized to drive a lot of the turbulence in the disk. And the turbulence is what imparts relative velocities to the grain. On Earth, in laboratory experiments, especially say in fusion, the tokamak fusion plasmas, they're actually trying to confine the plasma using very strong magnetic fields. And in that case, of course, the electrons and the ions are magnetized. They're tied to the field lines and they travel in very tight spiral orbits about the magnetic field lines. And so this will also change the charging of the dust. And then also will change the transport of the dust because the dust will now have a charge distribution, it's charged dust, and it will also interact with the magnetic field.
Okay, but it's what I didn't quite understand, in your calculation, do you take into account magnetic field? In this case, what are the topology you are assuming?
Right. In the stuff I showed here, I was not taking into account any magnetic fields. We have other experiments where we've actually put magnetic fields into the experiment on purpose, like when we were trying to simulate the formation of the lunar swirls. So these are dark and bright patterns seen on the surface of the moon that are associated with magnetic crustal anomalies. And we see that the dust transport is changed in the magnetic field. A lot of it is the ion drag because the ions are coupled to the magnetic field lines and exert a drag force on the dust. And we could actually reproduce these patterns that you see on the surface of the moon. And then also in Saturn's rings, the dust is charged, and Saturn has a really nice dipole magnetic field. And in that case, the dust, as it's traveling around the planet, is also having its orbit perturbed by the magnetic field.
Okay, thank you. So we have also another question from Barbara Jacek. Barbara.
Thank you. So I was wondering about the role of plasma instabilities in these studies. We know that instabilities are important also at the NIF. I guess up in space, when you can do this undisturbed, you minimize instabilities, but you must have calculated this.
Right. And so there's a lot of processes that can be going on in the plasma. And so you very rarely have this nice quiescent bulk plasma where the electrons and ions are perfectly in balance and there's no electric fields. So one of the instabilities that we see are, like I mentioned, that we actually have in the DC column, which when you look at it with your eye or even with the slow cameras on the space station, looks like a very homogeneous plasma that is very constant in time. You actually find out that on the short time scales, you have these ionization waves where you have blobs of plasma that are being created and then transported. And there's a lot of other wave processes that can go on in the plasma. And usually for the dust, people just assumed that you could ignore those because those time scales are very different from the time scales that the dust is responding to. But what we're actually finding is that it can change enough of the behavior because these are non-linear processes. And so you can't just do a straight time average because they don't add, they don't add in a linear fashion. And so the instabilities, if you actually model those and resolve them in time, will change the dynamics.
Very good. I think we can thank again Lorin here, and